Yeah, okay, I think we can start actually. So, yeah, I think just quickly, what I want to do first is to just do alternative um, method of rescaling H to H over 0. So, yeah, in the last lecture, we saw that um, we are interested in taking the limit of 1 over n in order to have a limit because we wanted to have these limits when it goes to infinity. This blows up. This does not exist the way we wrote it. We just change it to a limit of 1 over n and it goes to infinity. Trace of basically h over root n to the power 2. This does not exist the way we wrote it, but this, after the scaling, we got the limit, and we saw that the limit goes to the nth Kepler number, Cn, which is the nth Kepler. Here, Cn. Which is, we know is 1 over n plus 1, 2n chosen. And we saw that this leads to linear semicircle over here. So I don't write that. But there is another way to this scale. Instead of doing this, which is maybe is a bit awkward. So alternatively, scaling that I want to discuss is to change the partition function a bit. So this alternative scaling here is that, so we had this partition function Zn, which was equal to what? I mean, integral exponential of minus raised of 1/2 raised of h2 dh over hn, right? We got this partition function and work with that. Now, instead of that, we can work with, we just change it to, so for now, I just write Zn tilde, but it's usually called Zn again. But this time, we just say hn exponential of minus n over 2 trace of h2 dh. So physicists, also many mathematicians, prefer this scale. And it's a theorem. I mean, it's a simple lemma. You can show that actually if you use this, then you don't have to do this scaling here. So let me write it like this. So lemma is that the base Zn tilde actually the limit of 1 over n raised of h2m just per se, just by itself. This exists and it's a Cn. So you do the scaling at this level, and you get CM without any problem. Okay, so this I leave it as an exercise for you to go through the construction. You just see. One thing is that if you use, so maybe I just hint the proof. So in the usual, in the standard thing, the correlations were, you remember, the correlations were like Hij, HKL was equal to delta IL, delta JK, right? So this was the original correlations that we derived. But with this one, Hij, HKL, I call it delta. So if you use this to compute these correlations, you get 1 over n. Get 1 over n. Delta Ij, no, delta IL, delta JK. And you can see this 1 over L, then use Wick's theorem. So the crucial thing is to calculate again this propagator to be 1 over N delta IL JK. The original propagator is just 1 or 0. This is 1 over N over 0. So that's the difference. And that solves the problem. Okay. So that's all we wanted to do about the scaling, because in many sources you see this and appear here. That's very good. Any questions? So now we want to discuss, today we want to discuss unitary invariance. So today is unitary invariance and Weyl integration formula. Okay. So what we want to do, first of all, let me define this group UN, the n by n unitary matrices. So this is a compact Lie group. This is a compact Lie group. Its dimension is it's a real Lie group, compact Lie group. Do you know its dimension by any chance? Have you seen this before? Dimension is n squared. In fact, to see that, you can compute the dimension of its Lie algebra. So the Lie algebra of this guy is the set of skew Hermitian n by n matrices. Because if you have a curve of unitaries, you differentiate that identity, you get Hermitian. So this is Lie of UN is I HN. Hermitian skew symmetric. I mean, skew Hermitian n by n matrices. Skew Hermitian. And obviously, the dimension of this guy is n squared. In fact, you can write the whole Mn of C, the n by n matrices, complex matrices, you can decompose it. In fact, in a good sense, this is orthogonal decomposition even, but Hn is some I. So it's a Hermitian, skew Hermitian. You have this composition. This is 2n squared, n squared complex 2n squared, and this n squared plus n squared is 2n squared. Okay. So this is the,
Oh,
yeah.
sorry. So that's the dimension over the reals then.
Yeah, UN is only a real Lie group. It's not the complex Lie group. Yeah.
Oh, so it's different than the.
Yeah. You can complexify UN, then you get something else. But when
So it's
complex,
different than the SUN, I guess of the.
yeah, SUN, I write it. SUN is a subgroup of UN consisting of those. I'm
The
talking
connected
about
part.
group consisting of those unitaries whose determinant is one.
Yes, so it's the
UN is
identity
connected.
component.
UN is itself is connected. Yeah.
Yeah, that's so. Yep, thanks.
So this is SUN. U belonging to UN, such that determinant of U is equal to 1. Because we know that in general, the absolute value of determinant of any UN element is 1. So here we want it actually to be equal to 1. So the dimension is reduced by 1. The dimension of SUN is equal to n squared minus 1. It's always the case. Like in the standard model, for example, this is the quark symmetry, and that's 8-dimensional. 3 by 3 SU3 matrices. It's 8-dimensional. Yes. Anyhow, so that's okay. Okay. So now we want to discuss this. Okay, so let me now discuss the action of UN on HN. UN on HN. So if you have a matrix U in UN and a Hermitian matrix H, its action is defined to be U, H, U inverse. Maybe I should have here told you what actually unitary means. Unitary really means this. U star U equal to U star equal to 1, of course. I didn't want to write it. So this is U inverse is the same as U star. This is just conjugation action, which means anytime you change the basis in a unitary way, you implement this conjugation. Okay. So this action now, one of the things, for example, you want to understand is if the measure that we have on HN, is it unitary invariant or not? And this turns out to be the case. We'll prove it soon. So the measure d mu h, which is, do you remember, is 1 over Zn exponential of, now we just use the original one, minus 1/2 trace of H2 dH. This is unitary invariant measure. Is unitary. So you see the weight exponential minus 1/2 trace of H2 is unitary invariant because this trace of H2 is unitary invariant. So that's not a problem. But the fact that this Haar measure is also unitary invariant is not obvious. We'll see that. But even more important than this, we want to get to Weyl integration formula, which is crucial for us. So let me tell you what it is. Weyl integration. So the goal is to reduce an integral over Hn which is a space of n squared dimension. We can reduce it to an integral over a space of n dimension. We can write it as an integral over Rn. Well, we just call it f tilde of lambda, some weight function, which I put d of lambda. And then there is this Gaussian measure mu of lambda. So I will, as we go on explain, I'll just say for now, f for any invariant function. Well, what does invariant function means? Invariant function is a function that's invariant under the action of un. So in other words, we need this condition f of u h u inverse is equal to f of h for all. Here I should put a small u maybe. U inverse for all u in un and h in h. So what are some examples of invariant function? Can you give me examples of invariant functions?
Determinant.
Determinant is an invariant function, yes. Anything else?
Trace.
Trace is an invariant function. Anything else? So in general, examples of invariant function can take trace of hk or any k. This tracial moments we're working. These are invariant because this is, you can just say this is equal to trace of u hk u inverse. Just because of trace property, you can bring this from here. And then you can do this like this, trace of u h u inverse. Insert u inverse and u in between the two, and then u h u inverse, and then u h u inverse, and this is exactly obtained by acting by this u on this function. So any other functions you may think that are not exactly of this form? So this is for k equal to 0, 1, 2. So, well, you can take product of this thing, certainly. Trace of h k1 times trace of h k2 times trace of h kl. These are not of this form. Trace of product is not product of traces, but they are invariant again, right? And yeah, so you may want to characterize all invariant functions on Hn. That's a very good exercise. So I'll just give you this as an exercise. Find a description of all invariant functions on Hn. Because you mentioned determinant, where determinant is hidden among all this. It's not in the list. Find all invariant functions. on it. Yeah. You can take determinant square, for example, also. That's also. But it's well, this is a very valuable problem to solve to learn. Okay, but what we want to prove such a formula, which is really amazing because it means that we can reduce this integration because of symmetry. We can reduce the integration from dimension and square to dimension n of this function, which is f tilde, is very easily expressed in terms of f. And there is this weight function which will explicitly compute. And this works always. This is van der Waals term. So we'll work with it. Okay, now to prepare for that, we need a little bit of analysis. So let Hn circle be the set of all Hermitian matrices such that H has distinct eigenvalues. Because it has n eigenvalues, but there could be degeneracies. We reject degeneracies such that H has distinct eigenvalues. H distinct. So the lemma that I need is the following: this thing Hn circle inside Hn is open, dense subset of full measure. Is open, dense, full measure subset. Full measure means the following because measure of both. I mean, in the Lebesgue measure, they are both infinite measure, but in the other one, they are finite measure. Full measure means really the following: measure of Hn, if you excise HNO is equal to 0. Well, there is a question in the chat, I guess. My Zoom showed that it's not recording, is it? Maybe it's. I don't know. I hope it's recording. Oh, actually, I don't have to press recording. I don't have an option. Actually. Okay, so it's done by fields. Okay, good. Yeah. So now, how to prove this? So there are three statements we have to prove. Is that it is open, dense, and full measure. So full measure property, let me do it first. We need a proposition. The proposition is that let f from Rn to C be a polynomial map. I mean, non-zero. It's not identical. Then the set of zeros of f has measure 0. Set ZF of zeros of f is equal to 0 has measure 0. To prove this, so we can use induction on M. I mean, first of all, for n equal to 1, and this set is simply finite because you have a polynomial in one variable, and the set of solutions of this polynomial equal to 0 is a finite set. Right? Z of f is finite. And then, so it has measure 0. A finite set has measure 0 automatically. So in general, so let's do it. The induction step is a bit like this. So let's see how you can use, how can prove this for n equal to 2. So if you have a polynomial in, say, c of x and y, right, you can write f of x and y as sigma, say, pk x yk. Right? Some power. Then if you use the case n equal to 1, you can conclude that the set of zeros of f is basically it is of this form. For almost all points, so this is x, it's just a finite number of points over this x. And then for finite number of points, it's a full line. You can prove this using anything. I mean, for this, all of them has to be 0, then that's a finite set, and otherwise, one of them is non-zero, then. So you basically freeze the variable x, and then you argue using n equal to 1. Okay, then what you have to show, so this is the y-axis, what you have to show that if you have a subset of R2, which is of this form, what form? For almost all x's, the fiber over that thing is finite, and for finite number of x's, this is the whole line. This set has measure 0. You can prove that. It's not totally obvious, but you can prove it using Fubini's theorem. And the argument in general is like that. So I don't give the full argument, but it's just like that. So this is the case for full measure. Now, the case for being open is also not bad. So y is open. Well, we have to use something from algebra called discriminant. So discriminant is a quantity defined for a polynomial, right? So discriminant of a polynomial is a polynomial function in coefficients of f. So basically, product of lambda I minus lambda j squared, I less than j. These are roots of I different from j. Sorry, these are roots of this f, but this is a polynomial in coefficients of f. Is a polynomial function. Okay. Now, for something to have distinct eigenvalues, it means that this characteristic polynomial should have. So let me write the property of this delta, and delta of f is different from 0 if and only if f has distinct roots. Well, this from the definition is clear. F has distinct roots. Okay. So this is what we learn in undergraduate algebra, the property of determinant. Now, for a matrix has the distinct eigenvalues if and only if its characteristic polynomial has distinct eigenvalues. And we reduce the problem to this case. So let me write it here then. So H belonging to Hn has distinct eigenvalues. If and only the discriminant of the characteristic polynomial of f, which is determinant of h minus lambda I, this is the characteristic polynomial, is different from 3. So now what we can think of delta discriminant function going from Hn to C, and this Hn0 is exactly the set of points where this guy is non-zero and is a continuous map, first of all. And this Hn exactly is delta inverse of C minus 0. So this is open set, inverse of open set. Right? So this is not a step. So we use some basic algebra to do this. Now, the last property that I need to prove is that this guy is actually dense. So Y is dense. So in other words, we have to show that for any element in here in Hn and any closed matrix to it, there exists in any ball around it, there exists one non-singular matrix close to it. So for any H belonging to Hn, we can use a spectral theorem. And then we write H as U lambda 1 lambda n 0 0 U inverse for some unitary U and some eigenvalues lambda 1 lambda n of H. Right? Now, some of these may be coinciding. There may be repeated eigenvalues. What I can do, I can change this, each of them a little bit, or you just wiggle them a little bit so that they stay away from each other. And by that, we can just make sure that there is always a matrix, a unitary, a Hermitian matrix, which is very close to H and has distinct roots. And that's the end of it. You see, we can have something like lambda 1 equal to lambda 3, for example. They may all collapse, that there's degeneracy, and there's lambda 4 here. But then I can change that to, we can just perturb them a little bit. And this stays away anyhow. As much as you want, you can stay close to the original matrix in norm, and then that's because if you do this, the norm of the new matrix and the old matrix, they're very close to each other. This is clear. So this is density argument and the dilemmas. I need this now. So you may wonder why we need this. You will see it now why we need this to work with HN 0. Okay. So now right. So now for this Weyl chamber. So let's yeah. The n be the set of all n tuples lambda 1, lambda 2, lambda n such that lambda 1 is less than lambda 2, less than lambda, right? So the set of all real numbers that are increasingly ordered, we want to, and sometimes this is called Weyl chamber. So obviously this is an open subset of R, and this is like 1 over n factorial Rn, except for degeneracies. Okay, now let un tilde or un bar equal to un mod out Tn. This is the set of all u Tn, u belonging to un. This is the left coset space of Tn inside un. Left coset space of Tn inside. Now, what is Tn? Tn is the n-dimensional torus. The set of all e to the, so matrices of this form, e to the I theta 1, e to the I theta 2, e to the I theta n, theta I, the k belonging to R. Obviously, this Tn is a unitary matrix, and these are all the diagonal unitary matrices are of this form. All of them are of this form. Tn inside un. So this is the diagonal unitary matrices. This is called maximal torus. One of the maximal torus. There are many maximal torus. So I call it a maximal torus of un. Okay. So you'll see soon why we need this quotient space. Instead of working with un, we have to work with this quotient space. Again, whose dimension is n less than dimension of un. So this dimension of this un bar is equal to n squared minus n. Is dimension of this guy minus dimension of this guy, because it's a quotient. So this is a homogeneous space.
In general, would I guess the maximal torus be replaced with the Cartan subalgebra?
Yeah. In the Lie algebra language, you would work with Cartan subalgebra. Indeed, this is in the Lie group case, you work with these guys. Yes, exactly.
Oh, all right.
Excellent. Yeah, very good. Yeah. Okay, so now you will see why we need all this, in particular this HN circle and all that, because we want to study now a map which reduces everything to to the eigenvalue space, basically. The spiral chamber, basically, we're going to see it as the space of eigenvalues ordered according to the, for example, increasing order in this case. So let's consider the map. Phi from this map, basically the map of spectral theorem. Pn cross un bar to Hn sig. So what is this map? This map just multiply and conjugate, yeah, basically. So the map is defined like this: phi of an element here I denoted by capital lambda because it's eigenvalue matrix lambda, and a quotient here, an element in the coset. Put it in the bracket because this is just a coset. I just define it to be u lambda units. This is what we learned from a spectral theorem. You'll see why this comes handy now. Okay, first of all, this map is well defined. Well defined. This is a simple check. You can just check. You just take another representative in the coset space, same coset. You check that they match, and they do. So that's not a problem. Now this phi is surjective. So why phi is surjective? The proof is just a spectral theorem. Use the spectral theorem, right? If you have any emission matrix with distinct eigenvalues, you can always write it as, without even distinct eigenvalue, you can always write it as u, as we said, lambda u inverse. And you can order this matrix as if you want, that's fine. You order it and then you get this unitary. So being surjective, yeah, it's clear. Let's see, do I need to say it? So the claim is that this phi is actually a diffeomorphism. Phi is actually 1, 1 onto, is a diffeomorphism. Yeah, so we, by choosing this order, yeah, we are now, yeah, there's no chance of getting same matrices by different elements here because Yeah. Is this obvious to you? I mean, this being 1-1 on 2 map. No. Okay. So let me now tell you the strategy, what we want to do actually. You see, if we are sure, well, it is true that this guy is a diffeomorphism. You see, if you look at dimensions also match, because dimension of this guy is n, which is an open subset of, as a manifold, is an open subset of Rn. Dimension of this guy is n. Dimension of this coset space or homogeneous space is n squared minus n. And dimension of this guy is n squared. It's an open, right? So dimensions match, and you get the sense that they are same dimension. But I will give a little more argument why this is actually diffeomorphism, namely it's 1-1 on 2. But let me now give you the strategy of deriving Weyl integration formula. So we are looking at this map, right? So what we want to do, you have a function on Hn. So by composing it with this map, we get a function here. Now, if this is invariant, we can reduce it just to function here, because this unitary component becomes irrelevant. We get the function here. So all we have to do then is to compute the Jacobian of this map. And then we use just a Jacobi's change of variable formula, which will give us that weight function that I wrote, the van der Waals term. So all we have to do is to compute the Jacobian of this phi to reduce integration on Hn to an integration over the space on the left-hand side, multiplied by the Jacobian. Okay. So, yeah. Again, let me go back to maybe this this surjectivity and actually injectivity at the same time. How would you get these matrices U and lambda so that U lambda U inverse is actually equal to a given H? So the question is, given H, how do you find U and lambda such that H is equal to U lambda U inverse? How do you find this lambda? How do you find this U? How would you go? This is a linear algebra problem, right? So how do we do it? Well, we are going to compute the eigenvalues of H first. You get this lambda 1, and you order them because I know that they are distinct eigenvalues. It's lambda 1 less than lambda 2, less than lambda n. So you get these numbers. But now, how do you get U?
You can write the eigenvectors into it.
These are the eigenvectors, yes. So U actually turns out to be this V1, V2, Vn. These are the eigenvectors, and these eigenvectors are uniquely determined up to phase, because they have to be unitary. So they are only determined up to phase e to the I theta 1, e to the I theta 2, e to the I theta n. Now you see why we need, for this to be a diffeomorphism, we need to restrict to distinct eigenvalues. Because if you don't have a distinct eigenvalue, look, for example, you can have identity matrix, okay? In how many different ways you can write identity matrix like that? Well, you can choose any U. And then you just choose 1, 1, 1 for the eigenvalue matrix, and then for any U, this works. So this is not injective at all in that case. So to maintain injectivity, we restrict to the this thing on. So I think that's so now then so the crucial step to compute the Jacobian of this, which will so let me just prepare the ground. Maybe I go 10 minutes extra and then I will finish. Is that okay if I go 10 minutes extra? Okay, so anyhow, the thing is there. So okay, so how we are going now to compute the Jacobian? So computing the Jacobian. I mean, using a better language, we are basically computing the differential of this map. And we want to pull back the volume form on this space to corresponding volume form here up to some I mean what is this one? Okay, so we need a little bit of preparation. So let's consider an of C again that discussed. The dimension of this space over C is n squared, and over R is 2n squared, as I mentioned before. Now we're going to put a inner product here. So this is actually a Hermitian space. Hermitian inner product. And then of C. So basically, the inner product is A, B is equal to trace of A, B star. Sometimes this is called Hilbert-Schmidt inner product or Frobenius inner product, all these things. So to compute norm of a matrix in this inner product, for example, norm of Z squared, this is inner product of ZZ. Z is a matrix in C, which is trace of ZZ star. This comes out to be some ij from 1 to n, xij squared plus yij squared, where z, we just write it as zij, well, zij is equal to xij plus root minus 1 y. And this inner product is unitary invariant. So here's a simple lemma. Is unitary invariant. Because the unitary group acts here. And if you change this by action and change this by action, and that's obvious. So now we want to see this as a Riemannian manifold, as a very flat Riemannian manifold, like this. So as a Riemannian manifold, Of course, it's flat, but that's okay. I just want to use a little bit of terminology there, which is MN of C. The Riemannian metric, you can write it as ds squared equal to sum ij from 1 to n dxij squared plus dyij squared. So in other words, the Riemannian metric for this inner product in this coordinate is diagonal. So so Riemannian metric is okay. So this is it's n squared by is 2n squared by 2n squared. So then it means that ddxij's and ddyij's are is an orthonormal frame actually. An orthonormal basis for the tangent space of MMC at Z. So we know that if we have a Riemannian metric, we can take it the volume form, and we just take that volume form. So the volume form is product of dxij, product of dyij, ij equal to 1 to n. That's a 2n squared form. So that now we look at submanifold of this flat space. So one of them is Hn inside Mn of C, and the other one is unitary inside Mn of C. And so this is a Riemannian manifold. This is a submanifold, and the metric induces a Riemannian metric here, and also induces Riemannian metric. Okay, so we are interested in corresponding volume forms of those Riemannian metrics as they are induced there. So in this understood in this way, now you can easily compute the volume form of Hn. So the lemma is that not difficult. Is that the volume form of Hn is actually equal to 2 to the power n squared minus n, product of dxij, I less than j, product of dyij, and then product of dxii. That's the usual basis that we've been working with. I don't want. Right. So this factor is because now we are reducing the Riemannian metric to something which is curvy, unitary. And so basically, this is 2 to the n squared minus n dh, and this is the Lovec volume form that we were working with. This part we call it. Okay. I think now we are ready. So just 1 minute now. So again, consider this map reduction to the eigenvalue space phi from Dn cross U and bar going to UN, this diffeomorphism that we have. So yeah, now we want to compute the pullback of the volume form here to something here. So we want to compute phi star of pH. So if we can write, so this is a top form here, right, on this space. To compute the Jacobian of the map, I have to pull this back and then express this top form in terms of the standard top form here. So the standard top form over there, so this is equal to some function f of lambda and the u, right? Some function f of lambda. And then the standard measure, the standard form here is d lambda. And then there is this du bar. This is the volume form on this space, Dn, the Weyl chamber, which is just d lambda 1, d lambda 2, d lambda n. And this part is the volume form that you get on this cosine space. So this, now our goal is to compute this. This is the Jacobian in the classic language, not differential. This is the Jacobian. We want to compute that. So this, I will do it, yeah, I mean, I have to put here this one. I will do it on Wednesday. And then we'll see some amazing property of this Gaussian ensemble. Then we'll see that actually eigenvalues of a Hermitian matrix in the Gaussian ensemble, they repel each other. The eigenvalues don't like each other. They repel each other. They stay away from each other as much as they can. That's a crucial property of Gaussian GUE matrices. And a lot of beautiful things follows from this Weyl integration formula. Any questions? Okay, so looks like there are no questions. If there aren't really any questions, I'll just say bye and then I see you on Wednesday.